Hello, and welcome to the fourth video of the FP3 chapter, Integration. What approaches might you try for these integrations on the screen? Hopefully you've done the background work to be able to give the answer partial fractions, especially for this first one here, where we've got two terms in the denominator multiplied by one another. We can split this into partial fractions and integrate the two separately. Similar with this one here, you would look to factorize the denominator and then apply partial fractions. So partial fractions is a very useful method of integrating things of this form. But if you can't do that, you might have to complete the square. And if you complete the square, splitting it into partial fractions is not usually what then follows. Usually what you would then do is a substitution, or the usual standard integrals on your formula sheet. So if you've got a quadratic in the denominator, look to see if you can do partial fractions. If the denominator does not factorize, however, then complete the square and apply one of the things that we have done in the previous 3 videos. So here's an example. And that's it for the notes for the video. We've got 3 examples and then we're done. So the example here, in this sort of situation, normally I would take that denominator out and just work with the denominator initially, and then go back to the integral later. So this, I hope that you can do this fairly easily. We can complete the square, and that would be a minus 8. So the integral is going to become 1 over x minus 4 squared minus 8. And unlike the ones on the starter screen, this is not going to split into a partial fraction very easily. However, it is of the form something squared minus a number, which if you look on the formula booklet excerpt down here, is this one here. It isn't x squared though, and it isn't a coefficient in front of the x squared like we had on one of the previous videos. This is x minus 4 squared, but with a linear transformation, or I guess if you wanted to do it formally, you could do a simple substitution where x minus 4 is equal to u or something like that. You could turn it into this form very easily. And then apply this standard result. So here we've got 1 over 2a as part of the standard result. But be clear, the a here is not 8, a squared is 8. So a is the square root of 8, so we've got 1 over 2 times the square root of 8, which is 2 root 2, so I can change that to a 4 root 2, times the natural logarithm of x from the formula, but in this case we've got x minus 4 minus a, which is 2 root 2, all divided by x in the formula, which is x minus 4 in this example, plus a, which is square root of 8, and all of that plus c. So we've applied this standard result to this slightly different linear transformation here. And then if you wanted to, you could tidy this up a little bit, but seeing as these are surds and these aren't, I would leave it like that. Perhaps you could argue you shouldn't leave a surd in the denominator here, but I'm not too worried. Let's move on to the next example. So the same idea on this one. I'm going to pull the denominator out and see if I can put that into a better form, either by factorizing it or by completing the square and making it look like one of these down here in order to apply the appropriate result. So pulling that out, we've got 2x squared plus 2x plus 11, and that can become x plus 1 squared, 2 times that is 2, plus 9 to make 11. So I can turn my integral into 1 divided by, oh, I'm going to bring the 2 out, but I'll do that in a second. Plus 1 squared plus 9 dx. And then it's kind of looking like this one here. X squared plus a number. But there is a coefficient in front of this, so I'm going to pull that 2 outside and instead have 1 over 2 integral of x plus 1 squared plus 9 over 2. And then where the x here is x plus 1 here, and the a here is 3 over the square root of 2, I can apply this standard result and get an arctan. If the question said use the substitution, then I wouldn't be able to use the standard result. Of course, I'd have to go through the substitution process, but it doesn't, so I'm going to apply a standard result from the formula booklet. Don't forget that half in front. And we've got 1 over a. So a is 3, so I get root 2 over 3 times arctan x, which in this case is x plus 1, over a, which is 3 over root 2. And all of that is inside the arctan, plus a c. So I can tidy this up a little bit. We've got root 2 over 6 times arctan of root 2 x plus 1 over 3 plus c. And that is our final answer. For the last example, I'm going to impose upon myself that I do need to use a substitution. So I'm not going to use the standard result on the formula sheet, I'm going to go through the process. But I'll do the same thing. Starting point, I'm going to pull this thing inside the square root out. I don't like working with a negative x squared, so I'm going to pull the negative out the front. And if I complete the square here, I've got x plus 1 squared. And then I will want a 4, so we've got a plus 5 there. And don't forget, if you've got time in the exam, you can always expand these out just to double check if you're ever unsure that you've got the right answer there. So now I can change my integral. And I'm going to put the 5 first, and it's all inside a square root still. 5 minus x plus 1 squared dx. Okay, to use an appropriate substitution here, we've got something minus something squared inside a square root. If you remember the work we did on this, x plus 1 equal to, I think it's going to be sine is going to be the easiest, because 1 minus sine squared will give me cos squared, and if I differentiate sine I get cos. I think that will all cancel out nicely. But in order to make the numbers match, I'm also going to need a square root 5 sine u. And don't worry too much about this x plus 1, because obviously when you differentiate this, the 1 just goes to 0, and we get square root of 5 cos u du. So that plus 1 doesn't make much difference in this process. So my original integration here can now change to 1 over 5 minus 5 sine squared u, all inside of a bracket, and the dx becomes square root 5 cos u du. Just to make it clear for my examiner then, I could put it like this, and they all cancel out, and we get that really nice easy integral du, which of course is u plus c. Now we need to work backwards to find out u. From my original integration here, we've got x plus 1 divided by root 5 is sine u, so u is arc sine of all of that, x plus 1 over root 5. So my final answer is arc sine x plus 1 over root 5, or if you want to rationalize that you can, plus c. And there we go. Complete the square, put it into a format that you recognize, and either apply the appropriate substitution, or if you don't have to do that, use one of the standard results on the formula sheet. And you can practice these ideas using questions from exercise 4D in the textbook. And maybe I'll see you in the next video.